2 electrons, so it comes down, this happens 4 times, right? So you have this happening multiple times, right? You have pyruvate docking on here, transferring electrons to ferredoxin, transferring them to nitrogenase reductase, right? Binding ATP, right? There's only 2 binding sites on this molecule, right? But you have to keep on transferring electrons through and building up the capacity in this subunit here, right? In the coupled subunit, right? To successively form the unfavorable conformation, to kind of store it up and store it up and store it up to the point where, okay, finally I'm going to be able to reduce the N2. Right? Does that make any sense at all?
Could you say that again, please?
Sure. We've got delivery of electrons from pyruvate to ferredoxin to the reductase subunit, the green guys on the outside, right? And then those guys are binding ATP and facilitating an electron transfer onto this subunit. Okay? But they have to do it multiple times, right? They have to do it at least 4 times to transfer 2 electrons at a time, so that all the electrons can get to here, right? 8 electrons can get to here, so that finally you can drive this reduction of N2 to ammonia. Okay. As it moves these electrons through, it binds ATP, which allows electrons to come through to here, and the ATP hydrolysis here permits this reaction to happen. So the part that is a little unclear, at least to me, is you hydrolyze ATP here, right? You drive the formation of a protein structure, right? But you don't drive if it's just the first 2 electrons coming through, you don't yet drive the formation of a protein structure that's enough to let the whole thing happen, right? So one way to think about this is that every time you bring 2 electrons through here, you make this protein structure more and more strained till you finally get to the point where, you know, the triple bond can be broken by whatever force has to be brought to bear to break a triple bond. Right? This is the only place in nature where a triple bond gets broken, I think. Yes, sir.
Is the transition from, okay, I'm confusing myself. The process that turns pyruvate into acetylCoA in the bacteria that fix nitrogen, is that fairly similar to what occurs in eukaryotes?
Yeah, probably. I mean, pyruvate dehydrogenase complex would turn pyruvate.
Complex, or?
Well, I mean, that's what we learned about before. Is there a different kind of enzyme that can do it? I don't think so, but it's not really important for our purposes.
Okay.
Yeah.
Just curious.
Probably that's the same class of enzyme, same overall kind of enzyme. Other questions?
So I guess to take the last 30 seconds, so do you think the conformation change that leads dinitrogenase reductase to transfer electrons to the dinitrogenase
Yes.
is sort of another switch where once all 8 electrons are built up, and then ATP gets hydrolyzed, causes another conformation change to allow it to?
It's certainly building up electrons on this subunit here, on this reduced subunit, because this transfer is now 6 electrons for this and 2 more for that. So the electrons are clearly building up somehow, and the way they're building up is by virtue of the P cluster and that molybdenum cofactor.
Okay.
Right? But the details of that, I couldn't tell you.
Okay.
I mean, there are people who could tell you more about it, but I'm sure it's not fully worked out.
Thank you.
Yeah, the only other thing I wanted to mention is if we go into nature, we talk about crop rotations and such, and we're in a root nodule. The leguminous plants, like these guys, soybeans, alfalfa, clover, have these nodules and facilitate crop rotations. It's not hard to have the intuition that if you have O2, it's going to mess up these cofactors by oxidizing them inappropriately with these complicated electron transfer processes. I mean, that's generally true in many of these anaerobic organisms. the reason they can't tolerate oxygen is it interferes with electron transfer processes. The root nodules, though, actually have a variant of hemoglobin. It's quite interesting. It's called leg hemoglobin, and it's just bathing these nodules around the bottom of the plant, and it binds up whatever oxygen tries to get in. Right? So, by virtue of having that, it's a protective device that keeps the nitrogenase in the bacteria in the nodule, keeps the oxygen away from it, so that it can fix nitrogen and thereby provide ammonia to the plant. Okay. Final questions? All right, have a good weekend, everyone, and I'll see you on Monday.